Okay, so I was asked to speak about parameter inference, and yeah, so it's yeah, so gravitational waves is by now like a fairly mature field, even in terms of data, and there's a lot of data coming in and a lot of people working on it. So I don't know what is the distribution of people in this room in terms of their expertise in data analysis. So like, who of you spend most of your time doing data analysis? Okay, it's a respectable fraction of the room. So then my talk is likely not targeted at you. But there are people doing various kinds of maybe you're doing something else and you want to learn a bit about what's happening, what where the application of that in data analysis comes in. So hopefully this is targeted more at the second class of people, but of course maybe if you my goal is even if you're doing data analysis, hopefully you get a slightly different perspective on what you're doing. Okay, so let me start at the very beginning in terms of so right. So I want to start with a simple example that kind of illustrates the sort of things that you have to think about when you do data analysis. So let's start with an example that say there is a rare or semi-rare disease. Since we were talking about it in the morning, maybe it's Lyme disease, right? And uh, so let's say there's a test for this disease, right? And this test has the property that if you are sick, right, it returns positive 100% of the time, right? So a given person can be either sick or healthy, right? And if you're sick, right, it's completely unambiguous. So right, so this notation, right, so the vertical bar is saying it's conditional. So conditional on you being sick, the probability that it returns 1 is, that it returns positive is 1 and negative is 0, right? And if you're healthy, right, let's say the test has a 1% chance of turning up positive, right? Because it's not perfect. Right, so they sum to 1, right? So in this lecture, right, so I will be working with a conception of probability that basically you think that there is a stochastic process happening, and the probability is a function that is defined on the outputs of the stochastic process. And the interpretation is what is called the frequentist interpretation, which is this probability represents the relative fraction of the trials that end up giving that number, right, that output. So there are other interpretations, but this is like the simplest to conceptualize, right? So if you have a coin that you toss, right, so it's it's a fair coin. That means that if you toss it, like 100 times, likely the 50-50 is you'll get 50 heads, 50 tails, but there are fluctuations, right? So that's the conception of probability. But now let's say that you have no symptoms, right? But you just took the test anyway, right? And it returned positive, right? So how do you interpret that, right? Should you start writing your will, right? Probably not for Lyme disease, but hopefully not. But okay. So then so maybe you want to ask, what is the probability that you have the disease, given that the test turned positive, right? But this, so by the operational definition of probability that I assigned earlier, right, saying that there is a repeatable experiment and the probability counts the fraction that turned up, you gave that number, right? The probability that you're sick or healthy is a meaningless concept, right? Because there's only one of you, and you're either healthy or sick, and the result of the test is not, like, does not change that fact, right? You're either healthy or sick. Right? So it's just you don't know that answer, but it's not a coin flip. It's not a repeatable thing. Right? So you could say that, okay, it is meaningless. Either you're sick, so all that you can say given the axioms is that if you're sick, this is the chances, if you're healthy, these are the chances. Right? So okay, but let's say that you wanted a bit more, right? So if you want to make progress, you need some extra information beyond this, right? So the extra information, let's say that you're told that the prevalence of so there is a prevalence of the disease, right? So let's say that you're told that 1 in 10 to the 4 have the disease, right? So then this changes, so this you can use this information, but still this fact does not give the answer, right? So then you have to rephrase the question as not that what's the probability that I am sick. It's something slightly subtly different. You have to say that if you picked a person at random, right, and that person was out of the set of people in the world, and that person gave a positive test, right, what is the chance that they are sick, right? So it is slightly different, right? It's not, so you're viewing yourself not as an individual, but as a random draw from the collection of people in the world, right? So in that interpretation, right, so you want sick given positive, right? So in this interpretation, right, so then you can use the laws of probability to compute this. So by the definition of conditional probability, right, so this is the probability of sick and positive divided by probability of positive, and then you can write this the other way as P of positive given sick times P of sick, right? So this is this thing, right? And this thing you can decompose this as P of positive sick plus P of positive healthy, right? These are complementary outcomes. And then you'll write this as P of positive given sick times P of sick plus P of positive given healthy times P of healthy, right? Yeah, so viewing yourself as a random draw from the set of people in the world enables you to give an answer to this question, right? So now if you work this out, right, so positive given sick is, so this is 1, but I was told that the prevalence is 1 in 10 to the 4, so this is 10 to the minus 4. So this is 10 to the minus 4, and this thing is approximately 10 to the minus 2, right, because this is 10 to the minus 2, and this is basically 1. So this thing is only 1%, right? So you don't need to start drafting your will, right? So this apparently simple sort of exercise has several things in common with what we do when we analyze data from an experiment like LIGO, right? So how does it work, right? So you have some signal. So let's say this signal is defined by a set of parameters. I'm going to call it theta, right? And the model for how to get from the parameters to the signal, right, is what Patricia started talking about in the previous lecture, and we'll cover in more detail, right? So there is some deterministic map between the unknown parameters and the signal. And then there is, unfortunately, a source of noise in the universe. So no detector lives in isolation, right? And so the signal and the noise together talk to a detector, right? And then you measure the state of the detector, and then you get data, right? And this is an approximate idea in an experiment at LIGO. Actually, the measurement itself generates some noise, so there is a feedback loop and all, but that's too complicated for us at the moment. So we can just treat this as separate things. So in this picture, right? So what are the stochastic variables here, right? So the stochastic variables are the noise. So it is something that is random. And as consequently, because of the randomness of the noise, the data is also stochastic, right? But this is deterministic, right? And now the question of parameter inference is that you measure this data that is imperfect because of the noise, and you want to say something about the signal, right? So the parallel between this and that should be clear, right? So here, right, so the signal is like, you being sick, right? And the details of the test are in the noise, right? So once again, right, if you just view the signal as suppose there was just a singular source, singular event that happened, and that we have never seen any other gravitational wave in the world, right, you would have a problem in this way of defining probability, because you can't view the event as a, like as a representative of a population, right? So then you can't really apply this, this chain of thought. But then if you abandon the, this coin flip definition of probability, you can still, so in usually people still act as if the signal is stochastic, signal has some, just like there's a P of sick, right? So, you can still assume that there is a, some distribution for the properties of this, but once it's not connected to reality, right, the details become fuzzy, right? And so then the problem becomes arbitrary. I mean, so LIGO is nice because, by now we have seen, like 100 odd events, and soon to see, see many more of them, right? So we have a large number of, things that we have seen. So we have some idea of what is the, distribution of things in this space, right? And in fact, in the next week, you will spend some time learning about that. And therefore, we are not shooting in the dark, right? So we have, like, we have some idea of the prevalence there, right? So repeating the logic here, right? So you have P of, so here the sick is, parameters. Given the test being positive is the data. You would write this as P of data given parameters times P of theta. And there it was a binary choice, positive or negative. And now you have, sorry, sick or healthy, right? And here you have a continuum of parameters possibly. So the sum is replaced by an integral. So there is an integral d theta, P of d given theta times P of theta, right? So this equation is very analogous to that. And so this quantity here, right? So this is the, properties of the test, right? So this is called the likelihood. So sometimes instead of P, people write it as L of d given theta to emphasize that this is the likelihood. So the likelihood is an honest to goodness probability distribution, but it's a probability distribution over the values of the data if the true thing were theta, right? And this P in this interpretation here is the, just like it's the prevalence of the disease, right? So here P is the distribution. So, imagine that you were God and you knew, like, how the events are distributed in the parameter space, right? So P is that thing, right? Right. So this P is called the prior. And then this thing here, so this is a scalar. So it's not a function of theta. So because it's been integrated over. So it's not, it's just a normalization constant, but it is called the evidence. And this quantity here is called the posterior. Right. Yeah, so in the case of gravitational waves, right, so we are lucky enough to have many signals. And, so then this whole thing can still be interpreted in a frequentist sense. in the sense that probabilities mean coin flips. But of course, if you're like fully Bayesian in your way of thinking, you would even apply this apply this formalism to cases where you cannot view probability as a coin flips. As like for example, if you're measuring the mass of the neutrino or some cosmological parameters, it's unless you are like truly believe in that, right? So you can't really think of the universe as being like there are like many coin flips of neutrino masses, right? There's one neutrino mass in the world, right? So then the choice of so then this formalism doesn't really work, but then people still apply it anyway, right? So there is a prior, and so that's the Bayesian interpretation. Right? So but for this talk, right, we can still stick with the frequentist thing and work. But of course, this assumes that you know the prevalence, right? So here you know that it is 1 in 10 to the 4. But in reality, you only have imperfect, if at all, knowledge of the prior, right? And in fact, one of the goals of astrophysical inference from gravitational waves is to actually learn about the prior, learn about the distribution of events in the universe from many of them. And this is the task of population inference, which you will have a set of lectures next week. Right? So for this lecture, I'm going to assume that the prior is known. Okay. Right. Any questions, or this is too basic? Okay, good. So this, everything here is very general, right? So I haven't really defined what this likelihood is, right? And what sets the likelihood is, so because it's conditional, right? So theta is not, it's, for the likelihood, you can assume that theta is known. So then the probability distribution is set by the physical processes that are generating the noise in the detector, and your understanding of them either theoretical or empirical, right? So you define a likelihood, which is your best estimate of the probability distribution of the noise in the detector. And we only have imperfect knowledge of this probability distribution. Right? In fact, we don't know. Right? So we have some model, for example, people have some idea that there are, a short noise, there's radiation pressure noise and various processes, and then you can come up with a likelihood. But in the end, it is only like, you don't actually know what's happening in there. So this is, in reality, you should view the likelihoods that are used as only an approximation. Yeah. Yeah.
What exactly does that P of D given theta actually?
Yeah. In fact, yeah, I would think of P of D given theta as the thing that is most certain in this entire thing. Right. Yeah. In the hierarchy of ignorance. Yeah. Okay. Okay. So let's. So then we don't really know what P of D given theta is, but we can start with a simple model, which is like the spherical cow type of model for the noise, which is a pretty good approximation, but not 100% correct. We know that. So this is the so in this model, right? So the data D, which is measured, is the sum. So it is, first of all, this model is that the data is additive between the signal and the noise, right? So this is actually a very nice feature, right? So this H is the signal, and this is the noise, right? And this is the measured data. So this H of theta is the waveform model that you can treat of for the purposes of this lecture, you can think of it as a black box. It's like a function that you send in numbers and it spits out numbers, right? You need not know what they mean, but you can think that it is set by physics, right, by GR. And the noise is a stochastic process, so so this is the random part. So then in the you need a probability for the noise because it's a stochastic variable. So the idea, so in the Gaussian model, right? So the noise. So imagine that you have data that looks like this, right? So there is. Right. So let's say you measure the data. You measure data in some regular interval. So then you can treat this as a column vector. So n of 0, n of delta t. Right. So this is a column vector whose entries are random, and the Gaussian model is that the probability of these n variables, it follows a multivariate normal distribution. Right. So P of n is some constant. So it's okay. So here n is a column vector. So this thing, it looks like a row vector times. So this is n by 1, this is 1 by n, and this is n by n. Right. So it has n entries. And so this is sigma inverse. So I wrote this as sigma inverse. So the object here is the covariance matrix. So this is the inverse of the covariance matrix. The covariance matrix is also an n by n matrix. Right, so this is a very strong assumption and likely not correct fully, but this is a starting point. And Gaussian noise has several nice features that make it, like a good model to use. So some properties of Gaussian variables is, for example, if you want to evaluate the covariance between different components of this n, right? So this is just the ijth entry of the covariance matrix. So that's what these numbers mean. Okay, so this is the probability of the noise, and I want the likelihood of the data given theta. Right, so this is the likelihood. So this likelihood is like dp dd1 d dn. So this thing is just the probability I wrote there multiplied with a Jacobian factor, which is just 1 because it's additive. So it becomes unimportant, and this is just p of n1 and n, what I wrote out earlier. And often, instead of working with the likelihood, people like working with the log likelihood. Right, so ln L. So if I take the log at the determinant, so there is some prefactor, which I'm not going to write out, minus 1/2. So here, the things that are in the function are d and theta. So n here is d minus h of and so on. So this is d. So this is d minus h of theta whole transpose sigma inverse d minus h of theta. Okay. So this is nice because we can, like this is some mathematical thing that you can evaluate on a computer, right? So you can, there's some functions in here, and you just exponentiate it and you get the answer. And in practice, right, so this is the likelihood. What do you do with the likelihood? You plug this into here, right? And then you take a prior, which again, right? So next week will all be about how to infer what the distribution of things is. But for this lecture, you can assume that the prior is known, right? So then you can get the evidence, or you can get this posterior, right? So this posterior is some multidimensional probability distribution that is over the space of all these, parameters that define the signal. And in practice, right, what do you do with a ND posterior, an ND probability distribution, right? I certainly can't visualize it beyond 3 or so, right? So usually the posterior is, while it's a nice object, right, you don't actually use the posterior in itself. You look at various derived quantities based on the posterior. And so the main use of having the posterior is, you can think of that you want to compute integrals over the posterior, right? So in the end, all things that you query about the parameters, they can be reduced to some integrals. So d theta, p of theta given d times some f of theta, right? It would be something like this. So for example, if let's say that the posterior is one-dimensional, right? It's not, but let's say it is. So then you might be interested in, for example, the mean of the distribution, or you might be interested in the variance of the distribution, right? So they are all things like this. Or if you want to marginalize out some things, right, they're all integrals again, right? So then the real goal is to compute these integrals. But then, unless you have this posterior in closed form, which in the Gaussian noise model with the prior you do, right? But then you have to compute this unpleasant n-dimensional integral. And beyond the simplest integrals, right, you can't really compute these things analytically, right? So then the goal, while posteriors are nice objects, right? So in reality, we don't work with posteriors. We work with samples from the posterior, right? So what I mean is, instead of p of theta given d, you can imagine that you have some algorithm, right? Some black box that it keeps spitting out many samples, and these thetas are all fair draws from this posterior, right? So theta I, right? So then you use the theorem of Monte Carlo integration to say that an estimator of this integral is like 1 over n sam summation I f of theta I, right? So in reality, right, yeah, this is what you spend most of your time doing, right? So then there is a question of how do you construct this oracle, right, that you can query to keep giving samples from the posterior to compute whatever you want. So that is one entire set of schemes that you have to develop, or an algorithm how to do that, right? So there are various algorithms in use. And then the second thing is, given the typical, so all of this is fairly general, right? But given that you know that the h of theta is not some, like, I don't know, random thing that you do and that you can draw with freehand, unless maybe it is like a lensed object or something. Usually the waveforms have, like a nice structure, right? So that means that when something has a nice structure, that means that in some parameterization, it requires only a few numbers to describe it, right? So it is compressible. So then there's an entire sort of set of ideas of how to use that to speed up your computation of the likelihood, or the oracle's ability to generate samples, right? And in the next lectures, we will talk a bit about that. Okay. Yeah. Yeah.
Okay, what we know, like the line at the bottom.
Yeah, theta I is a draw from this distribution.
So does that theta inside the like
Yeah.
does that contain the theta 1, theta 2, theta n?
No, this is a probability distribution. And so this is just a, so really the thing here is a P, right? So for example, if I have a Gaussian, right? So then the Gaussian has some parameters describing it, and then it spits out examples of things that are drawn from that Gaussian, right? So if you, for example, take this theta I and make a giant histogram, right, it would look like this P. Yeah.
Here, noise is modeled as a multivariate Gaussian, but
Yes.
does that mean that noise at two different time steps are correlated with
We'll talk about that shortly. Yeah. Yeah. So here sigma is some arbitrary n by n matrix. I have not really defined what that matrix is. Yeah. So the properties of this matrix are that this matrix is symmetric, right? And it's also positive definite. So by that, I mean that it has eigenvalues that are positive, right? Or if you sandwich this matrix between two vectors, right, between that vector and itself, it's always a positive number. Yeah. Where are the, yeah, yeah. Okay, so I can, so these angle brackets are like the, so this is the expectation value over this probability distribution. Yeah.
I think I always have trouble reading like L and theta. So this is telling me the likelihood of my detector going off given some theta. So shouldn't I expect that to grow with my noise increasing?
So the exponential has a negative in front of it. So it falls. So more extreme values are less likely.
But so I think can you explain how to read L and theta? So am I reading this as like just the likelihood my detector gives me a signal?
No, not a signal, gives me the actual data that you see.
Okay. I understand.
Yeah. Yeah, it's a function of the data. Yeah. Okay. Yeah. Yeah, if you knew what the theta value was, right, so then there would be no uncertainty. But unfortunately, we don't. Right, so the different theta values are, for example, the theta values here, the theta 1, theta 2, theta n are, if you think of this uncertainty as being captured by a probability distribution, right? So the different thetas are like values that are drawn from the distribution, so they are compatible with the uncertainty. Does that make sense? Okay. Yeah, if you knew, right, if you were God, then you don't need to do this lecture, right? Yeah. Okay. Good. Okay. So I and in practice, right? So usually people simplify this a little more, right? So you can write this as d transpose sigma inverse t plus d transpose sigma inverse h So there are really two terms here, and I have said that both of them are equal because of the symmetry of this sigma matrix. Right, and usually you're interested in the likelihood. So you take this likelihood, right, and then the data is fixed, and you're interested in how it varies as a function of the theta. So then this becomes just a term that is, just another overall constant, that it's additive in the log, so it is a multiplicative constant for the likelihood. So these are the things where you really need to evaluate it. Okay, good. Yeah.
So H is a fixed physical model, right? Well, given parameters.
Yeah, H is a black box. Yeah, yeah. So H is a function, and H of theta is that function evaluated at a particular value of theta.
So H1, H, like what do the indices for H mean? Like are they different theta evaluations for the same function?
Yeah. So this is the signal, but in reality you evaluate it at some discrete points. So this is H1, H2. So okay, good. Right. So if this is all, like, if in a nutshell you wanted to know what goes on, right? Everyone is doing this thing, right? Everyone is always doing this. And then if you imagine that there's a black box that spits out these samples, you're in business and you can just treat it as a black box and work. But let's learn a bit more about how, how it's implemented under the hood. Okay, so first of all, right, so even though I wrote it out as a n by n covariance matrix, right, in the real detector, there is a feature of the noise that, that simplifies this property, which is that, so not only is the noise usually approximated to be Gaussian, it is approximated to be translation invariant. Okay. So what does that mean? So that means that, so you have some process that is generating noise in the detector, right? And then let's say you query the detector, from, I don't know, like, today morning, right? And query the detector 1 hour later, right? You get some other thing. Of course, point by point, this point will have a different value from this point, even though I suspiciously drew them to have the same curve, right? So this thing is not the same as this thing, right? So the realization is different, but statistically, they both look very similar. So what does that mean, right? So how do we encapsulate that mathematically? So the idea is that noise that is translationally invariant, the covariance matrix has a particular property, which is that these expectation values here are only functions of the lag between the 2 points where it is evaluated at. So n of t1, n of t2, which is, let's say, t1 plus tau, this is just a function of tau. Okay, so that means that if I take this expectation value here, right, and put the two legs, one leg here, one leg here, and move both legs by some amount, this expectation value does not change. So in the matrix form, what does that mean? That means that this matrix is constant along lines. Right, so all the values along this line are the same number. All the values along this line are the same number, and so on. Right, such a matrix is called a Toeplitz matrix. Okay, so this states, so the assumption is that the noise has this property, and in reality, it turns out that the noise is only approximately has this property, right? And and maybe Barak will tell you about it. I don't know what his plan is, but it's some. So you can think of it as, okay, let's say that I measure the noise. I can empirically test this. You can take LIGO data and empirically evaluate this, and then do it like 10 minutes later. right, with a lag of 1 second between these two legs, you'll find that the answer is more or less okay. Okay, it's more or less okay. But then you do the same thing at night instead of at day. The answer will be drastically different, right? Because the loggers who are logging, they are like sleeping at home near Livingston, right? So this stationarity is only an approximation. It's an idealization that might be valid for short intervals of time, but it's certainly not valid for arbitrary times. But it simplifies the calculation, so it's what we do again. Okay, so the C of tau is called the autocorrelation function. Right, so what is the autocorrelation function? It is the value. So you take the values along this diagonal, that is C of 0. Values along this diagonal is C of 1. Along this lower diagonal is C of -1, and so on. Right. So if I take the C of tau and plot it as a function of tau, what you will see is that it kind of looks like this. Okay. So it is peaked at tau equals 0, where at tau equal to 0, this is n square, right? So this is the variance. And as you go sufficiently far away, it falls off. Makes sense, it gets decorrelated the farther you go away, right? So this autocorrelation function is essentially, instead of defining n square numbers, right? So now it is only defined by n numbers, right? So you can imagine that it simplifies your life. I was just going to say that. Oops. Yeah, so from the way I drew the curve, you can see that, as Bruce was mentioning, this seems like an even function, and it is the case because we expect that the noise is time reversal symmetric, right? So then actually C of tau is only a function of C of mod tau. And also the data we are measuring is real valued. So C is real valued. So it's a real valued function. It's a real valued even function of lag. So then we can work with equivalently, we can work with C of tau or its Fourier transform. So what's the Fourier transform? So that's something that will end up being extremely useful for everything you do, right? So what's the Fourier transform? So you have, let's say, I've already used H and D. And let's call it A of t. Right, so there is some function of time, right? You can equivalently define it as a function of frequency, right? And so the relation between them is A of f is dt, A of t, e power minus 2 pi I f t, and okay, so this is an invertible transformation between the two. So in the space of vectors, you can think of this as a rotation, okay, as a rotation matrix. Okay, so the C of tau is like a square integrable function. It's a nice function. So this Fourier transform converges. So the Fourier transform of C of tau is called the power spectral density of the noise. Okay, so as I'll explain what this 2 is in a second, is the Fourier transform of C. So this is d tau, C of tau, e power okay. So for gravitational wave data, right, the data is strain data, which is dimensionless. So C of tau is the expectation value of the product of two dimensionless things, which is dimensionless. Right, Cs of f has units of time, right? Because it is integral d tau times a dimensionless thing, or equivalently Hertz inverse. Okay, so what from the properties that C is even valued and real, we can see from the definition that S also shares those properties, right? So S of minus f equals S of f, and S2 of f star is S2 of f. Right? You can work through the properties of Fourier transforms and you will recognize this, right? So just like C, you can only specify the right half, you could specify this only for positive frequencies. Thanks. Yeah. Okay. Right. So then you only need to specify one half and you have the whole thing. So usually people just sum the positive and negative things together and call it S of f is S2 of f plus S2 of minus f. Right. So this S of f is called the one-sided power spectral density. Okay. This is the two-sided power spectral density. So it's not super important that you wake up in the middle of night and you know what that means, but it's just when you're working with it, it's good to know. Okay, so this is the definition of S, right? For if you were learning this from a mathematician, this is how the mathematician would define it for you. And often physicists are very sloppy, so I will also be sloppy. And people use an alternative definition of S, which doesn't really make sense from the mathematical viewpoint, but it's easy to understand, which is, so first of all, the noise is not square integrable, right? So the noise, because a square integrable function dies down, right? But the noise is just ever continuing. So any integrals of this noise over time will not converge. They will just keep, like randomly building up. So, but let's say you pretend that the noise is square integrable, right? So yeah, if you were a mathematician, you would be very unhappy, but then you could work this way and everything will be correct, right? So then instead of, n of t, you worked with the Fourier transform of n, which is, in reality, it's not a convergent quantity, right? So then an equivalent definition turns out to be, so now n is real valued, but n tilde is a complex valued thing. So n tilde of f star n of f prime is 1/2 S of f, the Dirac delta of f minus f prime. Right, so this has the same information content as this, except this is maybe like mathematical gibberish. But this is how physicists generally write it, right? So this says that if n of f is viewed as a Gaussian random variable, first of all, a property of Gaussian random variables is any linear combination of Gaussian variables is Gaussian distributed, right? And in particular, the n of f is a linear combination of Gaussian distributed variables. So n tilde will also be Gaussian distributed, except if I evaluate the variance of any of the components, it's infinity. And that reflects the fact that it's not square integrable. But since we are physicists, we will just say we know what that means. Okay, so the fact that this is so this Dirac delta, in a sense, it enforces translation invariance of the noise. Okay, and here and you can check that the units work out, because n of f has units of seconds. So this has units of second square, which is Hertz to the -2. This is a Hertz to the -1, and this is a Hertz to the -1. Right, so it works out. So here the interpretation of this becomes a bit clearer. So if you think about, it becomes a bit clearer when you think about what is called Parseval's identity, right? So what is Parseval's identity? It's an identity in Fourier transforms, which says that, so the power of a signal is defined as dt a of t square. So this is called the power of the signal. And this, so Parseval's identity says that the power is equivalent whether you do it in time domain or frequency domain. So this is, right. If you think about what this means, it means that this transformation is a rotation matrix. So it's unitary. So it conserves the norm. Right. So now if I think about measuring the RMS sort of variance in the noise, right? So that would be something like this. And you can use Parseval's theorem to equivalently do it this way, right? And then this thing would give you S of f, an integral over S of f, right? So you can think that, let's say that you measure the strain and think of it as a Gaussian random variable and make a histogram, right? It will have a distribution and it will have a variance. And it's a scalar. In time domain, that's a scalar, right? And this thing tells you what frequencies contribute to that noise, okay? And so now this S of f, right? Again, I mysteriously told you what sigma is, right? As if we knew it, right? In reality, so if you had a perfect knowledge of how the detector works, you would know S of f. You don't need to, it's like experiment given. But in reality, S of f itself has to be estimated from the data because we have imperfect knowledge of how, of all the noise processes that are happening, right? So then there are algorithms to measure this S. Maybe Barak will go over some of them or something, or maybe one of them. And for our purpose, right, in your exercise, that in your exercise for this section of the course, right, you will go over that. So there's some algorithm. So if you're like scipy.signal. PST or mlab.pst, if you just think of it as a black box, it spits out an estimate of this S of f, and right, and you'll see the trade-offs in that. But now this S of f, if you take a section of data, right, just like as an external observer, just download a section of data and measure the S of f, you will see something like this. Okay, I'm not. Okay, you will see some curve, a bucket-shaped curve, and so this curve is a reflection of the various processes that are generating the noise in the detector and the measurement process and how it interacts with that. But from our purposes, it is just some function, right? You can just load it and work with it.
You're missing a tilde on your second n exact expectation value.
Okay. Thanks, Bruce. Bruce is very conscientious. Okay. Yeah, appreciate it. Okay, so this S of f is a reflection of the noise processes in the detector, right? And for our purposes, right? So this S of f exhibits a cliff. As f goes to 0, it really blows up. And beyond some point, the numbers you get don't mean anything because the data is not even calibrated at low frequencies. So in practice, you take the S of f and truncate it and then set it to infinity. So you can just imagine that at like very low frequencies, the noise is infinite. You can think of it like that. But that means that in the time domain, you're modeling the noise as having infinite variance. But that's fine because the signals you restrict to certain regions of the frequency band for your analysis. So in the last lecture, right, so there was a brief sketch where Patricia showed how the signals look like if you take h of t and Fourier transform it, right, this h, instead of looking at it as h of t1, t2, t3, t, right? So you can Fourier transform that, and you'll get something like this, like you saw that curve. So that means this S of f, right, it sets what part of the signal is actually measurable, right? So this means that anything that is below this cliff, right, the noise is so high that even though the signal is in there, it is buried and it is effectively unmeasurable. And all the part here like is where your ability to constrain the parameters come from. Okay. Yeah.
Do you mind us about those thin bumps?
What these things are? Yeah. Well, from our perspective, it's a black box and it spits out these bumps. But now if you ask me what are those things, like you go and ask the experimentalists and they will say that they are lines in the data. So there is some process that is emitting noise that is at a characteristic frequency where this function is orders of magnitude. Okay, that's gone. Where this function is orders of magnitude. So this is a log plot. I forgot to mention this is a log plot. So at this point, the noise is effectively infinite compared to these guys. And some of these lines are not even like noise. They are actually injected by the experimentalists. And they inject noise with a known characteristic and then measure it to see the response, calibrate the response of the detector. Right. So sometimes that experimentalists are nice enough to remove that noise that they have injected, but not always. Yeah, I think in the first observing run, it was not removed, so it is just there. But yeah, in later observing runs, then people recognize that actually, why are we including that in our analysis? We put that in, so they removed it, right? But yeah, so this is okay. Good. Okay. In the next 15 minutes or so, I will talk about things that are kind of annoying, but you should at least have thought about them at one point in your life. So I will talk about that, which is I'll talk about some signal processing stuff. Okay. So the point is I wrote these integrals as Riemann integrals over a continuous time. But of course, in actual data analysis, like your computer cannot store an continuous function, right? It stores a set of values. So in reality, you don't work with those things, but you work with what is called sampled data and maybe even bandpass data. So you need to know what that means if you're going to analyze the data. So I'll spend a little time talking about that. Hopefully not so much time, but let's see. Okay, so one property of the Fourier transform that maybe I should mention is the convolution theorem, which is very important in what happens next. So what is the convolution? So if you have, let's say, a of t and b of t, so two functions of time, and you can define their convolution, which is another function of time. So it's a function that takes as input two time series and spits out another time series. And this function is defined as okay. So this is the convolution operation. So if you want to think, so this is just a mathematical thing. If you want to visualize what is happening, this is like, so there is a of t, which is, let's say this is a of t, and let's say this is b of t. So this operation is saying that take one of these two, doesn't matter which one, flip it around, right? So I drew it symmetric, so let's make it not symmetric. Let's flip it around. So do it like this. So this is a reversed. And then you take this and multiply the two and integrate, and then you get one number. And then you move this to the right. And for each shift, you multiply and integrate, and you get another number, and so on. And you record all those numbers in a vector, you get another vector. This is the convolution of these two series. And this is a very important property because a lot of operations we do in data analysis, they can be phrased as convolutions. Okay. And the convolution has a nice property that, so in time domain, it looks complicated, right? If you think about it, if there are n numbers in A and B, this will involve order n square operations, right? But then there is a nice property of convolutions, which is that the Fourier transform of this guy, A convolve with B, Fourier transform evaluated at F, is the product of the Fourier transforms. And so if you have an algorithm, no, I have not. No.
Use time first.
Well, this is time flipped, right? Depending. If it is t plus tau, then I think it would be time reversed. Yeah. Okay. Right. So if you have a cheap algorithm to compute the Fourier transform, which is which is the fast Fourier transform, which is one of the most useful things in the entire thing, right? So then that takes some order n log n steps, and then this product is order n. So this convolution can be done much cheaper than in the time domain. So this is often very useful. Okay, so now let's exploit the property of convolutions to understand what happens when we analyze data actually. So the first thing that often happens is that I presented this a of t as a function with, basically it has infinite support. So it is, its value at all, like throughout the age of the universe. But in practice, right, you only hold a certain segment of data in your computer, right? So that is implemented as an operation called windowing. So that implies, so what does that mean? So you typically don't work with a of t itself, you work with a windowed version of a of t, which kind of looks like this. So this is a of t times w of t, where w of t is a window function, hence the symbol w. And as the name suggests, it only has non-zero values in a certain range of time. Right. So the simplest example of a window function is what is called the boxcar function. Right. So this is a window function which looks like, so it is 1 and 0 otherwise. So for example, if you're analyzing only 1 hour of data, right, it's like you took the whole data, which is present at all times, and then you multiplied with this boxcar function, right? So that's what you work with. So this is a seemingly trivial operation, but in frequency domain, it has very nasty features, right? Because what does this do? We can think about that. So this is a multiplication of two functions. So we can look at the reverse of the convolution theorem, right? Just like the convolution of two functions, its Fourier transform is the product of the Fourier transforms. The Fourier transform of the product of two functions is the convolution of their Fourier transforms, right? Because the inverse of the Fourier transform also looks like a Fourier transform. So you can just use the theorem. So for example, if this is not how actual data is, but let's say, imagine that a of t is Gaussian, right? So if I take a of t and Fourier transform it, a tilde of f, you might have learned that the Fourier transform of a Gaussian is a Gaussian. So a tilde of f, it's complex, but let's, for example, look at the mod, that it will also look Gaussian. But now, instead of the Fourier transform of this a, you actually work with the windowed version. So let's say that I only look at the data inside this region, and everywhere else is 0, right? So this is like a multiplied with this window function. So then the Fourier transform of the of this boxcar is the sinc function. Okay, so W tilde, so this is, let's call this WT. So this is the boxcar tilde of f. It looks like T times the sinc of pi ft. Okay, something like this. So sinc x is like sine x over x. So the sinc function, so the sine x over x, it decays as 1 over x, right? So this thing decays very slowly. So what that means is, remember in the Fourier domain, this A window tilde of f is like A tilde of f, A tilde convolved with A tilde of f convolved with W tilde of f. It's an abuse of notation, but hopefully you know what I mean, right? So that means that you take this Gaussian and then you convolve it with this. And this thing falls off very slowly. The Gaussian has exponential suppression, right? But then you're multiplying, you're convolving it with a window that falls off very slowly. So that means for a value that is for, for this frequency, instead of the thing being 0, right, or exponentially suppressed, you will get something that has very soft tails. You'll get something that, kind of looks like this. Okay. And this does nasty things, right? So this is something to keep in mind. And then there is an entire like sort of Wikipedia article filled with a bunch of window functions that instead of using this sinc, there's like industry of coming up with clever functions that fall off maybe faster than this, and then you use that, right? So, but then this function has a nice property that it does not touch the data inside, but all of those functions, they will sort of touch the data inside. So it is not, this is non-destructive while those are destructive, right? But it's a, it's a fact of life, right? So you have to live with that. And the second thing, the second operation that is done, which is also very destructive, is the operation of sampling. I mean, I already sort of secretly introduced you to sampling, because here I wrote this as A of t, which is continuous and function of the entire real line. But in reality, you work with like data that has been sampled at a cadence at a distinct interval, because I wrote A1, A2, AN. Right? If it is continuous, this would be an infinite dimensional. I mean, it's already infinite dimensional, but this would be like the quantum mechanics matrices that you see, right? Okay, so you would have, so when you do sampling, right? So you have some underlying data, which is like this, but that data is recorded at a particular cadence. So instead of this, you have something like this. Okay. So there is windowing, which is one effect, and then there is sampling, which is another effect. And the sampling also is destructive, right? So you lose information in general. So to understand what is happening, so you can think of the sampling, you can think of this as you take this underlying, let's say you have A of t, and then you multiply it with what is called a Dirac comb. So what is a Dirac comb? It's a infinite periodic sequence of Dirac delta functions. So there is an infinite sequence of Dirac delta functions. And instead of working with A of t, you are working with A of t multiplied with this. Okay. Comb of t, and this Dirac comb has a sampling interval delta t. Okay. So this Dirac comb, all the values in between are lost, and these values are like the weight of the Dirac delta function is the value that you're doing. Yeah. Oh, sorry. Yes. Thanks. Yeah. So now, so when you do this sampling process, so in time domain, it's easy to think about it, but what is happening in the frequency domain, right? So in the frequency domain, this multiplication, as Javier correctly pointed out, becomes a convolution. So then you take this nice Fourier transform you have, and then you convolve it with the Fourier transform of the Dirac comb. And I'm not going to prove it, but the Fourier transform of a Dirac comb is also a Dirac comb. Okay, so the Dirac comb, I'm going to call it DC. F, right? So this is it. What?
Same.
Oh, you have some notation for this?
Like three straight lines, horizontal.
Okay, let's talk about that later. Okay. So this is like 1 over delta t times the Dirac comb. So so now this is a function of frequency with a spacing, which is like 1 over delta t. Okay. But instead of, but instead of multiplication in the frequency domain, it's a convolution, remember, right? So it is very nasty. It's like you're taking this Fourier transform and then you're convolving it with this comb. So imagine moving this over the comb and integrating. So what that means is that the Fourier transform of this sampled function, it looks like the original Fourier transform, but then infinitely many copies of it, which are displaced by this 1 over delta t interval. Right, so there is this guy, this guy, this guy, this guy, this guy, this guy, right? So there's an infinite sequence, and the spacing is 1 over delta t, which is the sampling frequency. Okay. So this operation is not one-to-one. So that means that's another way of saying that this is destructive. Right. So this will lead to a loss of information. There is one case, there's a special case in which this operation it preserves information, which is when the original Fourier transform only extends within this half interval, within this interval. So let's draw these lines here. So these lines, so this is at half of this sampling frequency. So this has a special frequency. It's called the Nyquist frequency. Okay. So the Nyquist frequency is half of the sampling frequency. So if the original Fourier transform is non-zero only in this interval, then replacing it, all of these things, there is no addition here. So then this thing is invertible. You can just read off this and that's what it was. Right. So that is a famous theorem called the Nyquist-Shannon or theorem, which says that if the original function is what is called band limited, right? So then it can be sampled without loss of information. Right. So in frequency domain, it's immediately obvious how to do this, how to make this thing, how to take this thing and recover the original thing, which is read off the thing here. In time domain, there is some sinc formula, which is called the Whittaker-Shannon interpolation formula, right? But then the main point is that beyond this Nyquist, of course, real data is never truly band limited. Right. So if you just take the data from the detector, it will have all frequencies above, even where, you analyze where the signals have any power, right? But if you, before you, so a common practice that is often done, that is maybe one of the most important things to do, is if your signal falls off, let's say that the signal has 0 power here, then before you analyze the data, you band pass this data. So you remove all of these things. So removing this thing corresponds to multiplying with something in the frequency domain, which is convolution in the time domain. So it's called a low pass filter, right? So you apply a low pass filter, and then you downsample, right? And then you sample. But if you don't do that, let's say that you don't do that, then all of these guys, they will be convolved with these things and they will bleed off here, right? And then it becomes very destructive. Yeah, so it's not always, some people sometimes forget it and then it leads to bad things. Okay. So in reality, right, what that means is So I talked about two things. One is sampling and one is windowing. And in reality, you do both of them. So you window and sample, right? So then the continuous Fourier transform, it becomes a discrete Fourier transform after that. So the discrete Fourier transform is a version of this, except now there is a of I delta t, I equals n minus 1, and a tilde of m delta f is 1 over n delta t then m equals 0, 1, n minus 1. And the relation between a and m kind of looks like that relation, except it's like you did a Riemann summation and made it dimensionless usually. So this integral dt becomes summation over I, and integral df becomes summation over m, and the dimensions are absorbed. So a and a tilde, the convention is that they have the same dimension, but it's just a convention. Okay, so on a computer, you never do a real integral. You always do a finite integral. But this finite integral has all of these assumptions baked in, that you treated the data the right way before you did the analysis. And if you don't do it, then the answers you get will have some garbage in it. Okay. I think I'm over time, so I will pick up from here in the next lecture. I thought I would get further, but I think it's useful because this will help you in your first exercise. And then the goal is to have you know all the steps involved in doing the likelihood analysis that you usually do. Okay, thanks.